Hi, my name is Lian. Today I'd like to share my research work of pulsed-coherent lidar. Here's today's outline. First, I will do the brief introduction of the conventional lidar systems. Next, I will show the concept of the pulsed-coherent lidar, and at the end, I will show the measurement results and then show the conclusion. So lidar is a sensing system which uses light as a carrier to measure the distance. It has been widely used in many applications such as navigation system, environment assessment, and microtopography. It provides an important modality to 3D imaging. The market size of the LiDAR system is also growing fast with many potential applications, such as biometric security and industrial robotics. These applications bring the attention to the sophisticated sensor, which can provide fast scanning and high precision capabilities. Here we plot the state-of-the-art LiDAR system in terms of the precision and the sampling rate. In this plot, we can see that there is a direct trade-off between the precision and the sampling rate. In order to achieve high precision, it typically takes a longer integration time to improve the signal-to-noise ratio. On the contrary, to push the speed limits, we will sacrifice the precision. In this work, our target is to improve the precision and the sampling trade-off, which can achieve better than 10 micrometer precision and faster than 1 megasample per second sampling rate. Next, I will do the brief introduction to two kinds of the conventional LiDAR architectures. We can categorize the detection into two categories, either the direct time-of-flight detection or indirect time-of-flight detection. For the direct time-of-flight detection, which is also known as the pulse detection, the transmitter generates a pulse and emits the pulse laser. At the same time, it starts the counter to count the time of flight. After the signal bounces back from the object, the receiver detects the arrival of the pulse and then stops the counter. We then can convert the time of flight to distance by multiplying the speed of the light. It has an advantage of high sampling rate with one-shot measurement. However, the walk error, which is an input-dependent time offset, limits the accuracy of the measurements. For the indirect time-of-flight detection, one is called the phase detection, which is also known as the coherent detection or AMCW detection. Instead of sending a single pulse, a transmitter sends out a continuous sine wave, and the receiver detects the phase shift of the incoming signal. Then we can convert the phase information to the distance. It has an ability to achieve high precision. However, it has an aliasing problem that the measurement is confined in one cycle of the carrier. One solution of the aliasing is that we can lower the carrier frequency to cover the wider range. However, we need to slice the phase into a final step to get the same accuracy, therefore raise the requirement of the phase detector. A common solution is that we can do the segmented measurements. Instead of just sending one carrier, we can send out two carriers at the same time, one at low carrier frequency to cover the wider range, another one at high frequency for the phase detection. The coarse measurement quantizes the time of flight into cycles of the high carrier frequency. And once we know which cycle it is located, the fine detection takes over and we measure the phase shift within a cycle. This is an example of the segmented measurements. The transmitter has two laser carriers at two different wavelengths. Two laser carriers are modulated by two EO modulators separately, one at high frequency of 10 GHz, another one at low frequency of 300 MHz. The 300 MHz low modulation frequency measures the full range of the distance. Within a 10 GHz period, a high carrier frequency takes over the measurement with high precision. This segmented measurement extends the measurable distance by 32 times. However, the system has several drawbacks. First, the system burns twice the power since it uses two laser carriers. And secondly, two separate paths are used for the coarse and fine measurements. Therefore, the alignment is very challenging. Next, I will show the proposed pulse-coherent LiDAR system. The idea of the pulse-coherent detection is to combine the advantages from both the direct time-of-flight detection and the indirect time-of-flight detection. The pulse detection can provide a fast sampling rate, and the fast detection can achieve high precision. The CW laser source is amplitude modulated by a high RF carrier and a low frequency envelope modulation. To find the time of flight, the coarse time of flight is to count the arrival time of the envelope, and the fine detection is to measure the phase shift of the RF carrier. In the pulsed-coherent system, it only requires a single laser source and a single receiver channel. Also, the measurable distance can be further extended by simply increase the registers of the coarse counter. The transmitted format is shown on the left-hand side. The envelope modulation is on top of the RF carrier. Instead of transmitting a single pulse envelope, we can encode and extend the pulse sequence to do averaging. We can also encode a blank period to prevent multiple reflections. The detection algorithm is shown on the right-hand side. The overall time of flight detection can be partitioned into 3 parts: the coarse time of flight, the intermediate stage time of flight, and the fine time of flight. The coarse detection is counting at the rate of the low frequency envelope modulation, and the intermediate stage counts at RF carrier frequency, and the fine detection finds the phase shift within the cycle. This is the transmitter design. We have a 1550 nanometer CW laser. It is first modulated by a EO modulator at 19 GHz RF carrier. Then we inject the modulated laser to a comb to purify the noise. After the comb, we have a second EO modulator to do the envelope modulation at 140 MHz. And ETFA then amplifies the laser and sends out the amplitude modulated signal. The advantage of this transmitter is that it only requires a single laser source, therefore simplifies the optic design. Here we show the receiver design. Instead of 2 separate channels to find the segmented time of flight, we use a single channel for the measurements. After the echoed signal is received by the photodiode, and low noise amplifier amplifies the RF signal, and the mixer then converts the RF signal to IF. After the RF signal is sampled by the ADC, a complex digital mixer then down converts the baseband signal to DC. The segmented time of flight information then is calculated in the DSP. In this receiver, the segmented results are inherently aligned by the ADC's clock, therefore reduce the complexity of the calibration. Next, I will show the measurement results. To characterize the LiDAR performance, we first performed a 1D delay line scanning to characterize the linearity and the precision. A mirror target on the motor stage is placed at 2.5 meters away from the transceiver. We then submit 10 centimeter dynamic range with 1 millimeter step size. The overall distance results and the segmented measurement results are shown here. The maximum IL is 30 micrometer, where the arm's error is 13 micrometer. And the precision is 6 micrometer across 10 centimeter dynamic range. We also perform 2D scanning with a biaxial optic setup. The target is a gauge block stairs with 1 millimeter equipment at 30 centimeter away. The image on the right-hand side shows the scanning results. We also demonstrate the second optic setup with a MEMS mirror. A polarizing beam splitter is inserted between the transmitter, the MEMS mirror, and the photodetector. It improves the isolation of the transmitter and the receiver. We tilt the MEMS mirror to do the scanning. The scanning angle is plus and minus 5 degrees in both the X and Y direction. The scanned result is shown here, which is a UCLA logo with 1 millimeter depth. In this work, we report a LiDAR system with pulsed-coherent detection, and a segmented coarse fine detection successfully enhances the acquisition speed while achieving sub-10 micrometer precision.